Hello, welcome to video 43 in the lecture Advanced Mathematical Modeling. So today in this video I want to make the last excursion from the random walk business. Remember, actually we were discussing random walks to classify stochastic processes. Then we came across this super diffusive behavior, then we found these power law distributions. And now for several videos I was going into details and characteristics of power law distributions. And before we go back to the random walks, there's one thing I want to show you, which I think is a really important property of these power law distributions. That's this unexpectedness of large events. And what do I mean by this? And first let's first make here again the histogram of power law. We have random variables p of x, and let's take a log, and we have here our distribution which decays like this with the log binding. Okay, so that would be perfect scaling regime over several orders of magnitudes. Okay, so now and there's no two kinds of flavors of such power laws. Two flavors of such a power law if you go to real data, and this means either all the data is already there or the data is a function of time. What do I mean by this? Like either the data is there this means let's assume, for example, this x would be city size. If this is city size, and so which are this okay, maybe, and then here that's a histogram of city sizes, and that's our biggest city, maybe Tokyo, I don't know what's the biggest city in the moment in the world. And this means we know the biggest city because we see it here. We don't know, so we know the long tail. Here we know the distribution because we know the biggest cities in the world. It's very easy to see them. What we don't know so much is the many small communities, because there is so many of them, and who knows where all the small communities in the world are. Yeah. So if we have already all the data, or if, let's say, you take the word distribution, the distribution of words in the text, and then you open the book, and the first words you see will be the most common words. So again, we see all the data, they're already there, so we know the tail. Yeah, all data are there, and then we directly see the tail of the distribution. But the other flavor would be if the data is a function of time. This means, for example, so here examples would be city sizes or word frequencies. So we see all the data. If the data is a function of time, so let's say we have here time series. And here we have our distributions. And where would we have this, for example, with earthquakes? And then you have a certain spot, and then see we have a certain earthquake with a certain magnitude. Then later we have another earthquake with another magnitude, another earthquake. And then if we have such a time series, then what we will observe, it will be the here we will observe the left tail of the distribution, so the head of the distribution. Why is this? Because there are so many rare events, so mostly we will see only the rare stuff. And then maybe occasionally we see larger one here, but then we have again smaller ones, smaller ones, smaller ones. And if we wait long enough, and then suddenly we can have the big guy here as a surprise. So, trying to sum this up. So when we have these two flavors, if all data are there, then we see the tail. And if the data is a function of time, we see the head of the distribution. And why? Because like if all data are there, the most obvious events are the large ones. Here. But if we see only a small fraction, a small sample of the data at one time point, for example, if the data is a function of time, then we will typically see the values in the tail. We see only the small ones. I mean, you don't necessarily need a time dependence. For example, if for some reason we could only see some cities here, so let's say we have a big list of all cities in the world, and now we randomly pick a city and then want to know what's the size of the city, then we also would see only typically the small sizes, and then it would be hard to judge that there can be cities with such an incredible big size. But if we see all cities directly, then we know, okay, that's the big metropoles, the big communities. But if we have as a function of time here, we typically see only the small events, and then these really large events can then be unexpected. Very often then they're very unexpected, that suddenly we have this big event which is lurking in the power law. And so we have earthquakes, or where would this be in stock markets? And other things, if we have events which we get as a function of time, and then we look at changes in stock markets, or we look at the magnitudes of earthquakes, and so we typically in a small time window we see only the small events, and only very rarely the big ones. So now to give you an example of why this is so important, let's speak about earthquakes, and let's speak about Fukushima. You all know that we have Fukushima, we had this big earthquake. So in 2011 we had a big strong magnitude 9.1 earthquake in Fukushima in Japan. And you know that was all the problem with the power reactor, nuclear power reactor, because the power reactor was constructed, the power reactor was constructed to withstand a magnitude of 8.6 earthquake, but the earthquake had a magnitude of 9.1 and then destroyed this nuclear reactor. So now I make here a plot, a sketch of the plot of the histogram of the earthquakes in Japan. So here I made a plot. And this plot is a histogram of frequencies of earthquakes of a certain magnitude. So you see the magnitude goes here from 4.5 until possibly 9.5. So you know, in the Richter scale, the magnitude of an earthquake, it's a logarithmic scale. Yeah, so it's kind of the energy released in an earthquake. And so 4 or 5 magnitude is a minor earthquake. Something like 7, 8, that's all already serious earthquakes. And earthquakes of magnitude 9 or 9.5, I mean, these are really devastating earthquakes which really have a huge potential of destruction. And as I told you before, that's the Gutenberg-Richter law, that earthquakes are approximately follow power law, so earthquakes with higher magnitude are more and more rare. And this was the kind of histogram of earthquakes there in Japan, in this region near Fukushima, before 2011, before the big earthquake happened. And so you see there were quite a lot of small earthquakes. We have a kind of decay as a power law, and it goes until something like 7.4 or something. And then suddenly we see a change in the exponent. Suddenly earthquakes of higher magnitude decay faster. And now the question is, now you want to make a forecast. So you want now to know, okay, we have in this region, we want to make a nuclear power plant, so this should be really safe. And of course the question is, how much money should we invest in the power plant so that it can withstand a certain earthquake? Of course, now if you have enough resources, you can make a power plant which can withstand a very, very big earthquake. But I mean, this is unnecessarily resources spent if the probability is very small. And now you can do the following. So you can say, okay, let's make a scaling through the whole thing. So you could say, okay, small earthquakes follow here a straight line. They follow a power law distribution. But then for large earthquakes, something happens here, and then we have here this distribution. And then you can follow this distribution in the future. And then you could say, okay, if we follow this distribution, and then we say we want an earthquake, we want our reactor to withstand with a certain frequency an earthquake of magnitude 9 or 9.5. If you continue this forecast a little bit here, and then you could and then you say the chance, like this earthquake here of this magnitude would then appear in one earthquake in 10,000 years, and you could say, okay, that's a safe margin. And then you say, okay, we build an earthquake, or you could go for 1 in 10,000 years. They would be here in 1,000 years. So you say 1 in 1,000 years we have an earthquake of this kind of magnitude. And so that's what then the planners in Japan said. They said, okay, we make a reactor which can sustain an earthquake of this magnitude. And they went to magnitude of 8.6. and said, okay, that's earthquakes which are larger in magnitude are so rare we don't expect them to be, and so that was the margin they constructed for the nuclear power plant in Fukushima. But on the other hand, if we would have just followed our power law distribution, if we just would have continued this straight line, now it's hard for me to, by hand, to make this analysis. Then you see, for very large magnitudes of earthquakes, we come to a very different conclusion. So then here, for example, the probability of an earthquake of magnitude 9, if we follow our Gutenberg-Richter law, that's here more than an order of magnitude more higher. I think it was 700 times higher if you would follow a real power law distribution compared to this. Now, of course, in practice, it's always very hard to predict what's going to happen, because you just have this data. I mean, you don't see this rare event before it happened. And so very often then people, if they see the distribution, we see only the black dots, and people say, okay, there seems to be a kink here in the distribution, and then look for all kinds of reasons, and then they said, yes, of course, there is a certain geographic conditions in the sea floor around Japan, so that high magnitude earthquakes are more and more unlikely. And so they said, yeah, probably there is a kink in the distribution, and we expect that this high magnitude earthquakes are very unlikely. But then what happened? So there was an earthquake of magnitude magnitude 9.1, and this destroyed the nuclear power plant, and this was the surprise. Yeah? But if you know a little bit about power laws, I mean, this is not so unlikely, because like why couldn't you or why would it be a bit stupid to make here a straight line fit through these points? I mean, there didn't appear that there was not many data here there were not many data points, because like if you make the histogram, you make the histogram of all the events that happened, but even of magnitude over 7 earthquakes, there were not many events, and so you try to fit a line through something where there is not much data. Whereas the fitting in the small scale range, there was a lot of data, so here you could have a very good fit of the distribution. Now, of course, the problem is, do you now want to continue this distribution to very high events? Do you really believe that the Gutenberg-Richter law holds also for very high values? That's the question. Or do you think the power law holds only to a certain value, and then some cut-off function is valid here? But the problem is, just from these few observations from the largest events which had been seen, it would be very risky then to extrapolate this and say, okay, events of this magnitude are very unlikely. And so that's a systematic mistake or error that will always appear, because these large size events, they always then come unexpected, and they're lurking always in the power law. So the lessons here would be, you have always to be careful if you have such data, how you interpolate or parameterize this data. Do you want to have a distribution which has only this one parameter, this one exponent, or do you try to make a kind of better fit, but which in this case over parameterized the curve and gave a wrong expression about the probability of these large events? Of course, in hindsight, once the event was there, you could say, okay, now we have improved data, and then you can say, okay, probably the Gutenberg-Richter law holds for the whole range. It's really a scale-free property. But the thing is, in the real system, it's very hard to be prepared for these surprises. Yeah? So here, this was just this one example here with these earthquakes, where this maybe was rather everybody knows about Fukushima, but similar things you have if in other cases, for example in stock markets and so on, also where people then are really surprised when suddenly there is a crash in the stock market, because for a long time fluctuations in stock markets are rather minor, but suddenly you have this big event, everybody is surprised. But if you would look at the distribution, you would expect that these events from time to time can happen. Of course, all under the premise that you really have a power law distribution of your data. And so in some sense, these power law distributions make the typical statistics rather difficult. So remember, going back to the first slide in this lecture, you know, when we started to introduce probability, you remember? So I introduced probability as the likelihood of an event. So we wanted to quantify the likelihood, and then we said it's a ratio. And then we said, okay, in an experiment, we can just, if we have an experiment, we can just repeat the experiment very often. For example, we throw a pin, and then we see how often do we have a tail, divide this by the number of experiments, and this ratio very soon should converge to a number, and then we say that's the probability. But this doesn't work if you have a power law distribution. Because if you have a power law distribution, and if you want, you can do it simply in the exercise. So try to estimate the mean value of our distribution in such a way. So we take, for example, we have such a power law distribution, and now we say we want to estimate the mean value just as 1 over n. We take the first n events in our time series, and then just we sum all the x's that we have. Yeah? And then we are now, and so this will depend, so this would be our estimation for the mean of the distribution, but this depends on the sample size, of course. And when you do it for a normal distribution, so not normal, not in the sense of a Gaussian distribution, but a normally behaved distribution, so distribution which has not a long tail, like an exponential or Gaussian distribution, and we increase the sample size, we estimate the mean of our distribution, and this will first fluctuate, of course, and then very soon will converge to the real mean. And that's why how we can estimate the mean like this. But now if we have a distribution which has a long tail, if we have a power law distribution, and again we want to estimate the mean value, the mean size, for example, of an earthquake, and we sample many earthquakes. We want to know what's the typical value, and then we calculate the mean. It will also first fluctuate a lot, and then this quantity will settle on some value, but then by chance from some time you will find a very large event, and then we have a jump, and then this will decay again, but then you have again a jump. It will decay again, it jumps, and the whole thing will never settle to some constant, because if you just sample more and more, with some probability you will hit this very large event, and this will destroy your calculation of the mean, so you will always have fluctuations. If you use this normal way, as I also introduced it in the beginning slide, just repeat a large number of experiments and try to estimate typical characteristics from your distribution. When you have a power law distribution, this doesn't work. So the better way to do it, if you have a power law distribution, if you have a sample, make the histogram. From the histogram we try to extrapolate, try to fit our exponent alpha, and from this exponent alpha we know how to calculate the mean. Yeah? So beware, if your data are distributed as a power law, yeah, and the data is coming one by one in the form of a time series, so once by one new details of the tail of the distribution are unveiled, you have to be very careful of these surprises. Okay, that was now enough. I think I explained a lot enough about so typical properties of power law distributions, and now we can return to our random walks and look what does a random walker do if the increments are distributed as a power law. For the moment,